colleague, as well as Olga Krylia. So without their help, this work would not have been possible. What I'm going to try to do is just tell you a little bit about, I'll give you an overview of nitrides and why they're of interest. I'll talk about the substrate issue, and in particular I'll tell you about some recent work that we've been doing trying to grow gallium nitride on silicon, and some early success we've had with lithium gallium as a nearly lattice match substrate to gallium nitride. I'll then go and talk about some work we've been doing on MOCVD of gallium nitride as well as indium nitride. I'll talk about some chemistry that we've been trying to uncover, and finally I'll end with some work, some recent work that we've been doing on indium nitride. So with that, let's start at the beginning with the motivation for the nitrides. I'm sure most people have seen this plot of band gap versus lattice constant. The reason these are two important physical parameters is, of course, is that the energy gap is characteristic of the light emission wavelength, and the lattice constant is required because the lattice mismatch often deteriorates the material quality, and generally the devices we're trying to make are heterostructure devices, and we, if possible, like to do the lattice matching. So often we're doing band gap engineering, where we're engineering the band gap to select a particular wavelength of emission. At the same time, we're trying to match lattice parameters between active layers and, and confining layers to be able to go a higher quality device. In early, I guess in the 1960s, we saw the development of red light-emitting diodes based on gallium arsenide. They were further refined by adding aluminum, and it's a very common product. The price of an LED, red LED today, is on the order of a few cents. It's a commodity. Not too long after, we started developing phosphides, actually should be a phosphide, aluminum gallium indium phosphide, that gave very strong efficiency into the green region. So for many years we had red and green of the RGB, but we didn't have the blue. And it wasn't until around 1992 when Shoji Nakamura came along and demonstrated that gallium indium nitride, a active layer of a composition somewhere here, around slightly here, could get very efficient blue emission by forming a solid solution between gallium nitride and indium nitride. So with the advent of the gallium nitride based blue LED, we had the red, green, blue combination, and as a result we have the possibility then for an LED display. So some of the applications that have come up have all been, of course, based on the LED, because we now have blue, red, and green. But one of the first ones that was promised was the area of solid-state lighting. This is, for example, a headlight in a car, but there's also the possibility of replacing all the lighting applications that we have. The energy savings there is tremendous. It's one that is probably the largest market. However, the efficiency considerations, brightness considerations, and also cost of manufacturing have yet to realize it, except for niche applications such as street lights, signs, and automobile lighting. But the hope of the future is that the full spectrum of solid-state lighting will be accessible to gallium nitride-based materials. Of course, there's some efforts to try to make the ultimate device, which is the laser diode, which has applications in communications as well as in storage and other areas. One area, of course, very interesting to displays is the use of LED for backlighting. I think recently Samsung introduced a 46-inch LED backlit television that's now for sale in the commercial market. And as we've heard over the past couple days, it's a very large market to display, particularly important to Korea. The fact that gallium nitride has a very high melting temperature, on the order of about 3,800 degrees C, as well as a relatively low vapor pressure, and a wide band gap, is very suitable for applications that involve high temperature or high power. And you're starting to see commercially gallium nitride devices to be incorporated into power and high temperature device applications. More recently, there's been some reports of very high efficiency and radiation hardness, which is excellent in these materials, for the possibility of doing photovoltaics. The space being, of course, interested because of the radiation hardness properties. So the column 3 nitrides have a lot of potential. The market at this point has not been only a fraction, a small fraction of the potential. As I said, mainly limited to white light, the backlighting of LCDs, as well as the niche solid-state lighting markets. Some of the advantages of an LED over some other sources: it's very rugged, very lightweight, small, environmentally friendly. There's no mercury, other contaminants. Turn-on voltages are in the order of a few volts, so you don't have to have a lot of auxiliary electronics associated with it. Considerable design flexibility, almost instant turn-on. Lower energy consumption for solid-state lighting. Here's a comparison of the LED. Oops, it's about 7 times brighter than an incandescent light bulb, for example. The color temperatures and brightness are independent, and of course there's a long lifetime. This is a comparison of the lifetime of an LED versus, for example, fluorescent or incandescent light. What are the approaches used for white light-emitting diodes? There are basically 3 core approaches. The first one, the most obvious, of course, is now that we have the capability of generating red, green, blue LEDs, let's just combine them to produce white light. Tuning the frequencies and the powers, we can tune the CIE of the white and get excellent control over the color gamut. A common approach that's over here on the right-hand side is to take a blue LED, which is gallium nitride based, and on top of it put a yellow phosphor, a broad emitting yellow phosphor, which combined with the blue emission will give you a fairly good white light. Most of the white LEDs that you probably see now have a little blue tint to them. They're being made with this particular approach here. There's been some recent work actually in the US to try, and as well as Korea, to try to do a UV LED. Add a little aluminum to it, take it into the UV. This then opens up a wide range of phosphors that are available to do red, green, blue, so we would have a mixed phosphor excited by a UV photon from a gallium aluminum nitride LED, and then we can mix these appropriately and get a very nice white light out of it. Those are the 3 approaches. Most of what you see in the market today is over here. Okay, I'm going to now talk about 3 or 4 subjects. The first one I'm going to talk about is the substrate issue. The problem with gallium nitride was for many years. Actually, there was a lot of work going on in the 70s to try to produce gallium nitride. At the same time, people were working on zinc selenide in the hope of getting blue. Zinc selenide is where most of the work actually, early success was taken. Unfortunately, zinc selenide is a rather soft material, and the quality of the material has not been, well, was not very good. There's also a problem with doping and p-type. But with the advent of high-quality gallium nitride and p-type doping, the gallium nitride work had surpassed the zinc selenide. But there still is not a good substrate for gallium nitride. No one has yet successfully grown large area bulk gallium nitride on a routine basis at low cost, as we have with silicon or for gallium arsenide, for example. So there are basically 2 approaches, 2 general classes that one might take. One is to take an existing substrate, so sapphire is most common, silicon carbide. People have also investigated silicon, gallium arsenide, zinc oxide, a variety of other substrates, and just grow on the heteroepitaxially on the mismatched substrate. And that's currently what we are doing in the commercial applications. The problem with that, of course, is that the gallium nitride structural quality is not all that good. The defect, the dislocation density is on the order of about 10 to the 8th per square centimeter. It gets somewhat better with some effort, but it's compared to gallium arsenide or silicon, the dislocation density is extremely high. In fact, that's one of the mysteries of gallium nitride. How can we get devices that are so efficient yet have such a high density of dislocations in the material? Very surprising, but we do. One suggestion is that the low hole mobility, free hole mobility is responsible for that. It really doesn't have the ability to get to a dislocation or a grain boundary to recombine non-radiatively. Rather, it sits there and waits for an electron to come by. The other approach, of course, which is what's done often, is to do homoepitaxial, that is to find a gallium nitride substrate. And the two ways that people have approached it, one is to do bulk growth from the melt. Melt's awful high temperature, so solutions generally selected, finding an appropriate solvent, and to grow from the solvent has been attempted by several workers, and also to do sublimation, vapor transport to grow from the vapor phase. The other approach is to grow heteroepitaxy, grow then a very thick film by a fast rate, remove the substrate to leave behind a freestanding wafer of gallium nitride. So those are the two approaches. Even if you're going to go this route, you still have to go through the heteroepitaxy to start with your seed layer onto the handling substrate. What I'm going to talk about today, I'm going to talk about first some of our work with silicon, that is heteroepitaxy of silicon, which and I won't show today, but we've been doing some thick film gallium nitride on silicon. And then I'll also talk about growth on lithium gallate, which is almost nearly a lattice match to gallium nitride. So gallium nitride on silicon. Well, what are the advantages? Of course, silicon is an advantage. It's a very low cost, large area substrate, outstanding quality, zero dislocation density, easily doped NMP type, very good thermal conductivity, which is important for some of these device applications. And if we're going to integrate in some of the drive electronics, for example, very easy to do in silicon substrates. So there's a lot of motivation to be able to do gallium nitride on silicon. However, it does have an extremely large mismatch, 17%. The thermal expansion coefficient mismatch is different as well by quite a bit, 56%. So the relatively high temperature growth of gallium nitride, in order of about 1050 degrees C, produces a large strain, which then can deteriorate the quality of the gallium nitride. Also, people have not had very good luck growing gallium nitride. Gallium nitride will not grow on SiO2. If you remove the oxide and you start your growth and you're using ammonia as your precursor, you'll quickly form a silicon nitride, which again prevents high quality growth on silicon. So we took our standard approach. We tend to use a little bit lower temperature on our growth than typically, but our standard approach for doing gallium nitride on some other substrates was to grow using triethylgallium and ammonia at 850 degrees centigrade. When we did that, you can see we get polycrystalline gallium nitride. Not very good quality at all. It always resulted in polycrystalline material, only partially covered. We suspected that because we did a nice standard etch on silicon prep, that we had a silicon nitride layer forming. So, like a good chemical engineer, we went to use some thermodynamics. We estimated the phase diagram for the silicon, oxygen, nitrogen, gallium system. That was not previously known, so we had to use some techniques to estimate it. We used a program called ThermalCalc. And here is the low silicon mole fraction going out of constant gallium nitride composition phase diagram. And the thing I want to point out is, as long as we're below this monotectic line, we have only gallium nitride and SiO2 stable. Silicon nitride is not stable. So that suggested to us, if we keep our initial growth temperature down below this monoeutectic temperature, we should be able to avoid the formation of silicon nitride. Well, here's what we did. Again, comparing what we got at 850 to what we got at 560 degrees C, voila, we have single crystal gallium nitride of relatively high quality. So this technique obviously, or apparently, avoids the formation of the silicon nitride interface. This is further verified by high-resolution TEM micrograph that shows the lattice image of silicon 111. It shows a 2 nanometer 4 or 5 layer silicon oxynitride interface, and then relatively, well, of course with a small area, high quality gallium nitride C-oriented material. The selected area diffraction pattern shows that indeed it is single crystal, we follow through fairly well lattice match to the underlying silicon. There is this layer, this compliant layer that forms during the process. What we believe is going on is, even though we have a clean silicon interface to begin with, there is dissolved oxygen into the silicon, or perhaps we do have a little oxygen coming off the walls, but we form this silicon oxynitride compliant interface. If we go and look at the Sims analysis or profile across that interface, we see both silicon, we see both oxygen and nitrogen at that interface. And if we go look at XPS to look at the bonding structure, you see that if we expose it to ammonia, this surface, with our cleaning process, we get both evidence of silicon oxygen and silicon nitrogen bonds. We use only inert nitrogen. We have no evidence of the silicon nitrogen bond, although there's a little bit of residual SiO, either coming from the reactor itself or coming from just beneath the surface. So, as a result, we do form this SiO in solid solution, roughly perhaps equal molar of oxygen and nitrogen bonds, or close to it, that is able to serve as a compliant interface between the highly mismatched silicon and the gallium nitride grown upon it. We find if we get it too thick, it doesn't work. If we get it too thin, it doesn't work. If we change our temperature just above that 575 line, it doesn't work. It's a fairly narrow window where you do get the high quality silicon nitride credit. We've also looked at trying to do some other buffer layers. Now that by the way, was gallium nitride grown directly on silicon. There was no intentional buffer layer placed there. That silicon, or gallium nitride, I believe, is the highest quality gallium nitride that's been grown directly on silicon to date. It has a full width half max on the high resolution XRD, the 400 reflection of about 800 arc seconds. So it's a dislocation densities on the order of about 10 to 7 per square centimeter. So for direct growth on gallium nitride on silicon, it's considered very high quality material. It's the highest I believe it's been growing. Another approach is to intentionally go down there and put a buffer layer that's better lattice matched or perhaps softer that can serve as a compliant interface. The candidates, the ones I'm going to talk about today, are aluminum nitride, which is only has a slightly larger or smaller lattice parameter than gallium nitride, as well as zinc oxide, which is fairly closely lattice matched, a little over 2% mismatch, and boron phosphide, which no one has tried before. Boron phosphide is almost nearly lattice matched, and can also be grown epitaxially on silicon. We had a previous, I'll talk to you. So we took some aluminum nitride, we grew it on gallium nitride by hydride VPE, using the chloride of aluminum as well as ammonia at 1,000 degrees C. And we come back and grew in our traditional commercial MOCVD system at our typical growth conditions. And you can see indeed we get single phase, single crystalline gallium nitride. If we go look at the quality of the gallium nitride, it is relatively high. In fact, it's the best gallium nitride we've grown yet on silicon. Here's a TEM micrograph of the silicon showing the aluminum nitride buffer interface and the subsequent gallium nitride, which is fairly high quality. There's some dislocations extending from the surface through to the surface, but this has proved to be, to date, our best approach to getting silicon on aluminum nitride. Another approach was to use zinc oxide. Zinc oxide is fairly closely lattice matched to gallium nitride. The problem with zinc oxide, though, is it's fairly unstable. And thermodynamic analysis indicates that above about 600 degrees centigrade, the zinc oxide will blow off, will thermally decompose, and we really won't have the buffer layer to grow upon. So that suggests, in fact, here's some preliminary experiments we did with ammonia treatment. At 850 C, we see no evidence of zinc oxide. The zinc oxide just dissolved into the gallium nitride and underlying silicon. But if we keep the temperature below about 600 degrees C, we can retain the zinc oxide at the interface. Here is just a low resolution XRD scan of gallium nitride grown with the higher temperature. We get very poor signal relative to the underlying silicon, the gallium nitride. However, doing the low temperature buffer layer growth of gallium nitride on the zinc oxide produced a smoother surface morphology as well as a much higher quality gallium nitride. The zinc oxide was put down by pulse laser deposition. Interestingly, it grew C-oriented regardless of whether we were using 111 or 100 silicon. Very surprising. The quality of the zinc oxide, or gallium nitride grown on the zinc oxide, however, is not as good as that was grown on aluminum nitride, or even that was directly grown using the in situ oxynitride interface. We had a program trying to grow cubic boron nitride. Cubic boron nitride, as you may know, is a very difficult material to grow. It's very hard. It is also easily doped, and so it was suggested for the ultra-high temperature power electronics using diamond boron phosphide interfaces to develop PN junctions. Our approach, one of the approaches we tried to grow cubic boron nitride was to first grow boron phosphide. Boron phosphide is relatively easy to grow. We use boron trichloride and phosphorus trichloride or phosphine. And we're able to grow successfully boron phosphide on silicon. Also, boron nitride or ammonia should reduce boron phosphide to form boron nitride. So we took some of our boron phosphide that we had grown by CVD, and we tried to grow directly at high temperature without a buffer layer, the gallium nitride, and the result was very, very good. We got single crystal gallium nitride, fairly high quality, and you can see strong O02 reflection as well as the O04 reflection. And this has encouraged us to consider or to continue on with boron phosphide as an interfacial buffer layer. So I think work that we've been doing over the last few years of trying to grow gallium nitride on silicon is very promising. And eventually, I think for some device applications, silicon may become the preferred substrate. We've also been trying to, once we take this fairly high quality gallium nitride on silicon, to go and grow very thick films of gallium nitride. Now this is on the order of a few hundred microns. And then to remove the silicon and leave behind freestanding gallium nitride. I won't show you the results, but I'll report that we have successfully grown thick gallium nitride on silicon without cracking. And so that's a fairly good result. Part of the result is having that compliant layer, but it's also a result of us using a lower growth temperature and therefore incorporating less thermal expansion strain energy. All right, I'm going to move now and I'm going to talk about growth on lithium gallate, LGO we call it. And so the idea here is to first grow a seed layer of gallium nitride onto LGO using traditional techniques, and then come back and grow very thick by hydride vapor phase epitaxy, a few hundred micron gallium nitride, and then to remove the substrate. Okay. So people have tried all these substrates to date. They've tried these techniques, not all to each substrate, and there's a variety of techniques people have used for removal of the handling substrate. The approach I'm going to talk about is LGO as their substrate, a MOCVD buffer layer, and then hydride VPE growth of thick gallium nitride. And what's going to be unusual is that conditions are chosen right and the interface developed correctly, we can get the gallium nitride to release automatically from the underlying LGO substrate without any removal, and the LGO substrate can be reused. Here's the crystal structure of LGO. It's an orthorhombic, but it's nearly hexagonal and a very small mismatch to gallium nitride. Some results that compare what were some of our first attempts. We would take as received LGO. It was just being produced and it was not available commercially when we started. You can see the top surface is not crystalline. There's a lot of damage. When we would grow, we would get as received. The polishing procedures were not in place. However, we found that if we would do a nitridation of the interface, and this is the LGO, this is an interfacial layer, and then we would have gallium nitride going on that. But if we went in and just did a nitridation of the LGO, 850 degrees C, we would form this very thin, on the order of about 20 angstrom, lithium gallium oxynitride compliant layer. And not only that, which is very unusual, we would see that the underlying LGO would actually epitaxially grow, either from deep in to the surface most likely, to leave behind single crystal lithium oxy gallium nitride on top of single crystal LGO. And a real nice interface. We were also worried about lithium diffusion into the gallium nitride. This layer here served as a nice barrier. We saw no evidence. In fact, we estimated the lithium diffusivity at about 10 to the minus 17. Some profiles that we took. But the key to this technology, again, and this is a theme that's recurring, is to be able to do interfacial engineering. To be able to design that interface to be compliant, to serve as a barrier layer, to be able to, I'm going to show you, it will also self-release with a small amount of strain that's put in as a result of cooling. And doing that correctly by design, perhaps as you saw, just using the thermodynamics to choose an appropriate temperature. Once you get that interface properly designed, you then can go and use traditional techniques for growth. Here's some MOVPE gallium nitride micron film that we grew on top of it. This is the lowest voltage half max we've ever recorded for gallium nitride of about 21 arc seconds. That's approaching the quality of gallium arsenide. And so here's a high resolution, not high, low resolution TEM micrograph showing the cross section. We had to look pretty hard to find a few dislocations. Next job then was to grow a very thick gallium nitride in the order of about 200 microns. We did this using hydride VPE, but redesigned one. In traditional hydride VPE, we'll take HCl, pass it over liquid gallium to form gallium monochloride, and use the hydride ammonia as your precursors for for CVD. We took and combined MOCVD with hydride VPE in the sense that we took trimethyl gallium, which is an organometallic, reacted it upstream with HCl to form the gallium chloride in a hot wall reactor, and we then had the subsequent, in the deposition zone, it looked like a hydride reactor. In the source zone, it looks like an MOCVD system. And so we combine the best of both designs. That is, we can get rapid reactant switching, we can get clean sources, but at the same time we get the high growth rate of hydride VPE, and we also get the impurity, low impurity concentration advantage of having chlorine in the system. In addition, the HCl or the chlorine in the system helps lower the cracking temperature for ammonia and allows you to go a little bit lower growth rate or growth temperature at the same quality and growth rate. The process we ended up with was one in which we took our handling substrate, and I'm talking about LGO at this point. We put this reaction layer, this buffer layer, this interfacial layer that we designed. It was the gallium lithium oxynitride. We grew a buffer layer or barrier layer using traditional MOCVD at about 850 degrees C. We then went into our thick growth during hydride VPE. Interestingly, when we grow hydride VPE, we become nitrogen terminated. Whereas when we grow MOCVD, we're gallium terminated, so we get a polarity switch when we switch growth techniques. The nitrogen terminated surface grows very rough, so we would have to come back and grow a capping layer by MOCVD to revert back to the gallium terminated phase and to grow a nice smooth surface. When we do that, we can produce freestanding gallium nitride. This was produced back in I think about 1998 actually. We produced it. At the time was the world's largest piece of freestanding gallium nitride. And very high quality. That piece has a full width half maximum of about 47 arc seconds. What's really interesting is it's self-separating. That is, when we cool in the reactor, the LGO, thick gallium nitride on top of it, we would pull it out, and the gallium nitride would be freestanding, and you just lift it right off. And looking at both sides of the gallium nitride, it was separating between the oxynitride buffer layer and the gallium nitride grown by MOVPE, which allowed reuse of the relatively expensive LGO substrate. Okay, I'm going to switch gears here one more time, and I'm going to talk a little bit about CVD and some chemistry work that we've been doing. There are basically two chemistries used in almost any CVD. One is to use a metal organic precursor, which then undergoes irreversible thermal decomposition and produces a large driving force. It was developed in the early days to do epitaxy on foreign substrates. Hydride VPE is a reversible chemistry. It's a reversible reduction of halides, and is actually the first chemistry that was developed. And as I said, it usually gives a much higher growth rate, about maybe 100 times higher growth rate than you can get from CVD. So here's a system. Here's a system. And I'm going to skip through a couple of slides and just tell you about what we're doing. We have developed a reactor that has a Raman spectrometer outfitted to it. And in this spectrometer, we can measure temperature and concentration profiles by looking at the Raman scattering signal, or in some instances, we've been using laser-induced fluorescence. Then we've developed a model, a full two-dimensional model of the reactor to be able to take the measured profiles and solve the inverse problem to estimate rate constants, cross-sections, diffusivities of our species. And with also identification of species, which is helped by computational chemistry, we can develop reaction mechanisms. So, as a chemical engineer knows, a CVD reactor is nothing more than a gas-solid reactor that's operating under fairly reasonable or easily modeled conditions. The problem is that we really do not have the kinetics, quantitative rate parameters and mechanisms to be able to go in and do a chemical engineering design of a reactor. So we set about correcting that by putting this reactor together. And I'm going to step through some of this stuff. Just tell you a little story. The story is trimethyl gallium decomposition. It was well known that ammonia decomposition is well known. The first step is a very slow step, form NH2, and after that it proceeds fairly rapidly. But this has been well studied over the years, and rate constants are out there and well known. Trimethyl gallium was studied in the 1970s. It was thought to undergo a sequential homolytic fission of the carbon-gallium bond, produce the dimethyl, this being a rate-limiting step, and quickly the monomethyl, which is relatively stable, and it would subsequently be converted to the element, each time giving off a methyl radical. Well, that was pretty much the state of what was known about trimethyl gallium decomposition. And so we set out to study it. The first thing we did was look at ammonia decomposition, which I said is fairly well known. Here is the temperature profile. Here are the compositions measured. And indeed, when we come back and estimate the rate constants, you can see for the first step, we did very good agreement with what's in the literature. We also then looked at trimethyl gallium decomposition, and consistent with other in situ measurement that was in the literature, we get a much lower start temperature extending over a larger temperature range, which would give you a different rate than that measured by an in situ Rexet techniques such as mass spectrometry. But we were able again to identify the rate constant for breaking that first carbon gallium bond. But that's not the whole story, because what you'll find out is that ammonia decomposes very slowly. It requires a high temperature. Whereas gallium, trimethyl gallium, begins to thermally decompose around 200 degrees C. But yet we're able to grow. In fact, that was the breakthrough that allowed I believe, the first LED, blue LED, to be drawn, was that there was a reactor design change that allowed trimethyl gallium and ammonia to be delivered in a way that could react at the surface and produce gallium nitride at 1,000 degrees centigrade. And what was going on is what we discovered is that the trimethyl gallium and ammonia at low temperature in the inlet region is actually forming an addict. This addict compound then can undergo further reaction by attack of the trimethyl gallium to form an oligomer, a polymer, and this polymer can coat out on the surface. It also undergo an intermolecular reaction to produce the same oligomer. So what we have going on is a balance between not forming this polymer, because the polymer then takes gallium out of the reaction, but we want to form the addict because it's going to preserve the gallium and the ammonia, preserve the gallium for delivery to the surface, where then it can undergo reversible decomposition back to trimethyl gallium and ammonia, and we can deposit out gallium nitride. So very complex. If we allow this reaction to occur, we'll form a polymer. It takes gallium out. If we allow this reaction to perform, it forms gallium in the vapor phase. Also takes gallium out of the reaction. We need to deliver to the surface this addict, and we need to find conditions to do that. Here's some examples of how we discerned this mechanism. This was a spectrum taken, measured compositions or relative intensities for the trimethyl gallium, the polymer, as well as the addict, as a distance from the susceptor. So this is the hot wafer for deposition. This is our inlet stream. What we did, first of all, we took and we formed the addict only upstream, and then under its own vapor pressure, we transported it in ammonia, nitrogen, and look what happened. So we have the addict coming in, and at about this temperature, which is about I think about 250 degrees C, the trimethyl gallium ammonia addict starts to decompose. At the same time, you start to see the polymer appear, but you also see trimethyl gallium start to appear, because it's undergoing the reverse reaction back to trimethyl gallium and ammonia. Well, once the trimethyl gallium starts to appear, it also starts to attack the addict to form more oligomer. And eventually, we reach the point where the trimethyl gallium then will start to decompose itself back to monomethyl gallium, and that's what's being delivered, trimethyl gallium and monomethyl gallium, to the surface. This polymer is not participating in the reaction in any way. The real system, here are the results. This is trimethyl gallium, well, it's trimethyl gallium, the addict and the oligomer again, but with a mixture of trimethyl gallium, ammonia, and nitrogen. That is the real reacting system. So what happens is, if we look at the trimethyl gallium, we're feeding in trimethyl gallium, but it's starting to disappear, even before, at low temperature. This is really close to room temperature. And what's happening, of course, is it's starting to form the addict. It's, in fact, it's starting to form the addict, and removing that. The trimethyl gallium then will attack the addict and start to form the oligomer. Even at this very low temperature, you see you get the oligomer formation. Once we get to the hot zone, we then have the release of trimethyl gallium from the addict. It starts to disappear, and then we even get and as a result, the trimethyl gallium being present, and with the addict we get additional oligomer form. Now that we know the kinetics, now we have rate constants, we've gone back, we've done the reactor design problem. What temperature, what flow rates, what kind of reactor design do you need to be able to preserve the gallium in the addict formation and deliver the most gallium and ammonia to the surface for subsequent reaction. So I think a good example, I think, of chemical engineering working. Step through to the last. We've been doing some work on indium nitride. Indium nitride, this is pure indium nitride. There's been almost no work done on this. Indium nitride is difficult to grow because it has a fairly low thermal decomposition temperature, about 700 degrees C or so. It starts to thermally decompose. It's also difficult to grow at that low temperature because of the ammonia decomposition. Forming a solid solution with gallium nitride is difficult too. because it forms, it's immiscible. Its solubility is only in the order of about 10 to 20% on either side of the phase diagram. To complicate matters further, there is uncertainty today about what the band gap energy of indium nitride is. It's been reported in the range of 0.7 eV to 1.9 eV. You would think at this day and age that we would actually know the band gap of indium nitride, but we really don't. Obviously, it can be varied. So this opened up to us the possibility of doing RGB in a single material. And that is, we could do indium nitride with a little bit of gallium added back into it, up to maybe 10%. We could get red and green if we could understand how the band gap varies. This would be 0.7 to 1.9 variation. And then add gallium nitride with indium nitride, a little bit of indium nitride back into it to get the blue, as we do today. So we have the possibility of doing RGB involved. And so we've been doing a lot of work on growing on that. I'll just end with one slide. One of the things we did was be able to grow it. We had to get rid of the indium droplets that would form. We did that by adding HCl to the system very nicely. But in fiddling around with this, we found that under certain conditions, we could grow nanorods. These are very nice hexagonal solid nanorods of indium nitride. And so we're working on these materials now, and just last week we put a sensor together that was able to detect hydrogen at various parts per million reversibly, and was not sensitive to oxygen and some other molecules. What was really nice about this was the low power. This is the lowest, one of the lowest power room temperature hydrogen sensors that has been reported to date. So with that, I want to thank you. I think the future is bright because gallium nitride is going to light the world up. And I'll be happy to entertain your questions.